of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Will the history of astronomy be divided between before Webb and after Webb?
Yes, I believe it will be.
Astronomers continue to explore the origins of the cosmos, striving to uncover the secrets of the first stars and galaxies. While much remains unknown, they are inching closer to understanding with every groundbreaking discovery. This is the remarkable conclusion drawn from the unprecedented findings of the James Webb Space Telescope. After completing its first year of observations, Webb has revolutionized our ability to study the faint infrared glow emitted by the universe's earliest luminous objects. By peering back into the first few 100 million years after the Big Bang, Webb has provided more detailed data about the birth of galaxies than any instrument ever created. But its discoveries have exceeded expectations. The sheer number of young galaxies it has uncovered in the early universe is astonishing, far surpassing predictions. To date, dozens of such galaxies have been identified, leaving scientists amazed. Astrophysicist Charlotte Mason from the University of Copenhagen expressed the widespread surprise. "We truly didn't anticipate this." In response to Webb's observations of unexpectedly mature galaxies from the universe's infancy, researchers have rushed to explain these findings. Could these anomalies be due to errors in the analysis of the telescope's initial data? If not, can they be reconciled with standard cosmological theories? Or perhaps these observations hint at an even more complex and mysterious universe than previously imagined? Could it even challenge the Big Bang theory itself? To fully grasp the situation, let's revisit the early days of the universe's formation. Following the Big Bang, the young universe began to cool. Over the course of a few million years, the chaotic plasma filling space stabilized, allowing electrons, protons, and neutrons to combine and form atoms, primarily neutral hydrogen. This ushered in a quiet, dark period known as the Cosmic Dark Ages. Then something transformative occurred. The majority of the universe's matter, composed of an elusive substance called dark matter, started to play a crucial role. Dark matter, which is invisible and interacts primarily through gravity, had a significant impact on the cosmos, particularly in its early stages. According to standard models, cold dark matter referring to slow-moving, unseen particles scattered throughout the universe unevenly. In regions where dark matter density was higher, it began to collapse into clumps. These clumps attracted visible matter, composed of atoms, which also cooled and eventually condensed to give rise to the first stars. The radiation from these newly formed stars reionized the previously neutral hydrogen during an era known as the Epoch of Reionization. Through gravitational forces, larger and more intricate cosmic structures formed, ultimately creating the vast network of galaxies we observe today. Meanwhile, the universe continued its expansion. In the 1920s, Edwin Hubble discovered that the universe was expanding, and later, in the 1990s, the Hubble Space Telescope provided evidence that this expansion was accelerating. The universe can be visualized as a loaf of raisin bread. Initially, it starts as a mixture of flour, water, yeast, and raisins. As the yeast ferments, the loaf rises, much like the expanding cosmos. The raisins in the loaf, representing galaxies, move farther apart as the loaf expands. Observations from the Hubble Space Telescope revealed that the loaf is rising at an accelerated pace, with the raisins separating at a speed that surpasses their gravitational pull. This rapid expansion is believed to be driven by a repelling force known as dark energy, symbolized by the Greek letter lambda. By incorporating values for lambda, cold dark matter, and ordinary matter and radiation into Einstein's general theory of relativity, scientists have developed a model to describe the universe's evolution. This model, known as the lambda cold dark matter model, aligns closely with most cosmic observations. To validate this model, astronomers look at distant galaxies, which is akin to peering back in time to the universe's first few 100 million years. During this simpler era, the universe's progression can be compared to theoretical predictions. The first attempt to observe the universe's earliest structures was made in 1995 using the Hubble Space Telescope. Over 10 days, Hubble captured 342 images of a seemingly empty patch of space within the Big Dipper constellation. What astronomers discovered in this dark region was astonishing: a multitude of galaxies at various distances and stages of evolution, stretching back further in time than expected. Hubble identified some extraordinarily distant galaxies, including GNZ11, discovered in 2016. This faint galaxy, estimated to have formed 400 million years after the Big Bang, was incredibly early in the universe's history. Despite this, the lambda CDM model remained intact since GNZ11 was exceptionally small, containing just 1% of the Milky Way's mass, and appeared to be unique. However, astronomers required a more advanced telescope to determine if GNZ11 was an anomaly or part of a broader trend of early galaxies, which could uncover missing components of the lambda CDM model. This led to the creation of the James Webb Space Telescope. Positioned 1.5 million kilometers away from Earth and shielded from heat by its massive sunshade, the telescope features a segmented mirror and highly sensitive instruments. It was built to reveal unprecedented details about the universe's early moments, and it delivered. Within weeks of full operation, Webb exceeded astronomers' expectations with groundbreaking discoveries. The telescope has uncovered galaxies formed near the dawn of time, analyzed exoplanet atmospheres in remarkable detail, and captured stunning images of planets within our solar system. However, its mission is far from over. By exploring the universe's first few 100 million years with unmatched precision, Webb is poised to redefine our understanding of how the structured universe we inhabit emerged from the chaotic beginnings of the cosmos. The groundbreaking discoveries of the Webb telescope could reshape the initial chapters of cosmic history, revealing insights not just about distant galaxies and epochs, but also about the origins of our Milky Way. Mark McCallgreen, a senior advisor for space exploration at the European Space Agency, emphasized that these advanced instruments are designed not to validate existing paradigms, but to challenge them in unpredictable ways. To measure the distance of celestial objects, scientists rely on a version of the Doppler effect, similar to determining the location of an ambulance based on its siren's pitch. As an ambulance approaches, its siren sounds higher in pitch, and as it moves away, the pitch lowers. Likewise, galaxies moving farther away from us have their light stretched to longer wavelengths, appearing redder, a phenomenon quantified as redshift, or Z. The redshift value indicates how far light has traveled to reach us. One of the first studies using Webb's data was led by MIT astronomer Naidu and his team, whose algorithm identified a galaxy with an unusually high redshift and brightness. Initially called Glass Z13, its redshift was later revised to 12.4, and the galaxy was renamed Glass Z12. Other astronomers also reported redshift values ranging from 11 to 20, including a galaxy named Sears 1749, whose light is thought to have traveled for 13.7 billion years, just 220 million years after the Big Bang. These discoveries hinted that the widely accepted lambda CDM model might need revisions. In the early universe, galaxies weren't expected to grow so massive so quickly. According to Chris Lovell, an astrophysicist at the University of Portsmouth, early galaxies shouldn't have had enough time to form many stars or undergo significant mergers. A November study analyzing computer simulations based on the lambda CDM model found that Webb's observed early galaxies were significantly more massive, about 10 times heavier than the galaxies simulated to form during the same epoch. While some astronomers and media outlets suggested that Webb might be breaking cosmology, not everyone agreed. Part of the challenge lies in the complexity of lambda CDM predictions. While the roles of dark matter and dark energy are relatively straightforward, visible matter is governed by intricate interactions that are difficult to model, especially during the universe's chaotic early years. These conditions must often be simplified in simulations. Another challenge is accurately determining the distances of galaxies. As Webb's data has been refined, some of the initially reported high-redshift galaxies have been reclassified, placing them in later stages of the universe's evolution based on updated calibrations. Despite these adjustments, Webb continues to expand our understanding of the cosmos, challenging long-held assumptions and providing new avenues for exploration. Sears 1749, for instance, lies in a region of the sky that hosts a galaxy cluster emitting light from 12.4 billion years ago. Naidu speculates that Sears 1749 might actually belong to this cluster, potentially being a nearer galaxy filled with dust that creates the illusion of a higher redshift. Regardless of its exact distance, Naidu described Sears 1749 as unusual. It represents a new type of galaxy we haven't seen before, small and low mass, yet somehow packed with significant amounts of dust, which is unexpected, he explained. This raises the possibility of previously unknown galaxy types perplexing researchers in their quest to understand the universe's distant realms. Determining precise distances, however, relies on Webb's most advanced tools. While Webb observes starlight through photometry, which measures brightness, its true strength lies in spectroscopy, which analyzes light's wavelengths. To draw an analogy, photometry is akin to capturing a face in a crowd, while spectroscopy is like performing a DNA test to trace family lineage. Naidu and other researchers studying massive early galaxies initially used brightness-based redshift estimates, essentially identifying faces in the crowd with an exceptionally high-resolution camera. However, this method is far from conclusive. At a January meeting of the American Astronomical Society, astronomers joked that as many as half of the galaxies identified solely through photometric methods might require reclassification. To refine these estimates, cosmologists began combining photometry with spectroscopy. By early December, researchers from the Webb Advanced Deep Extragalactic Survey, otherwise known as JWST, used this dual approach to analyze 4 galaxies. They focused on a specific spectral feature known as the Lyman break, where the light spectrum cuts off sharply due to hydrogen absorption in the intergalactic medium. As the universe expands like an ever-rising loaf of raisin bread, the wavelength at which this break occurs shifts, enabling astronomers to determine the galaxy's distance. By detecting redshifts as high as 13.2, the JWST team found evidence of galaxies whose light originated 13.2 billion years ago. Kevin Heinlein, an astronomer at the University of Arizona, recalled the jubilant reaction. It was pure elation. "Oh my God, we did it, we did it." These spectra are just the starting point for what I believe will be groundbreaking discoveries in astronomy, remarked Brant Robertson, a JWST astronomer at the University of California, Santa Cruz. According to Robertson, the findings suggest that the early universe underwent rapid transformations within its first billion years, with galaxies evolving at a pace 10 times faster than they do today. He likened the phenomenon to a hummingbird, a small creature whose fast-beating heart sets it apart from other animals. The heartbeat of these early galaxies occurred on a vastly quicker timescale than that of a galaxy like the Milky Way. But could this rapid evolution outpace what lambda CDM can explain? As breathtaking Webb images captivated the public, researchers began delving deeper into whether these galaxies conformed to lambda CDM's predictions or simply adjusted the parameters that refine its calculations. One of these crucial parameters involves the masses of the earliest galaxies. Cosmologists estimate a galaxy's mass by analyzing its brightness, though Megan Donoghue, an astrophysicist at Michigan State University, cautions that this is, at best, an informed guess. The calculation relies on assumptions derived from known stars and well-studied galaxies. A central assumption involves the initial mass function, which describes the statistical distribution of star masses at their formation. This parameter is vital because hot, massive blue stars emit more light, while most of a galaxy's mass resides in small, cooler red stars. However, the IMF in the early universe may not have been the same as it is now. If this was the case, the seemingly massive early galaxies observed by Webb could be much less massive than their brightness implies, bright, but lightweight. This potential discrepancy complicates things because tweaking the IMF, a fundamental input for lambda CDM, could yield almost any result. Chris Lovell observed that some astronomers consider altering the IMF to be almost heretical. Wendy Freeman, an astrophysicist at the University of Chicago, added, "If we don't fully understand the IMF, understanding galaxies at high redshift becomes an immense challenge." Freeman and her team are conducting observations and simulations to better constrain the IMF across different environments. Over time, many experts began suspecting that adjustments to the IMF and related factors might reconcile JWST's observations of ancient galaxies with the lambda CDM model. Rachel Somerville, an astrophysicist at the Flatiron Institute, expressed optimism, stating, "I think it's more likely that these observations can fit within the standard paradigm." According to Somerville, what the findings reveal is the astonishing pace at which dark matter halos could gather gas, cool it, and form stars in the early universe. Perhaps the gas was denser, she speculated, Maybe it flowed in more quickly. We're still unraveling these processes. Somerville is also exploring whether black holes influenced the early cosmos. Astronomers have observed some luminous supermassive black holes at a redshift of 6 or 7, around 1 billion years after the Big Bang. It seems almost unimaginable that stars could have formed, ended their lives, collapsed into black holes, and consumed enough material to become radiation-emitting giants within such a short time frame. However, if black holes existed within these early galaxies, they could explain the galaxy's intense brightness despite their relatively low mass, Somerville explained. Evidence that lambda CDM can accommodate some of the early galaxies observed by Webb emerged just before Christmas. A team of astronomers, led by Benjamin Keller at the University of Memphis, examined several major supercomputer simulations of lambda CDM universes and found that these simulations could replicate galaxies as massive as the 4 spectroscopically analyzed by the JWST team. These 4 galaxies are notably smaller and dimmer than other proposed early galaxies, like Glass Z12. According to the team's findings, all simulations produced galaxies matching the size of the JWST galaxies at a redshift of 10. One simulation was capable of forming such galaxies at a redshift of 13, which aligns with JWST's observations, while 2 others could produce them at even higher redshifts. Though these galaxies lack the overwhelming mass needed to challenge the model, they exhibit intriguing traits. Heinlein noted that the stars within these galaxies appear free of heavy metals from previous star explosions. This characteristic suggests they could be population 3 stars, the long-sought first generation of stars in the universe's history, and they may have contributed to the universe's re-ionization. If true, Webb has already captured a glimpse of the enigmatic era that set the universe on its current trajectory. Despite conforming to broader cosmological principles, the early universe was unusually bold, radiant, and fast-moving. Leah, a co-author of a recent study, said, "The objects we're discovering are as massive or larger than the Milky Way, which is astonishing." Her paper described 6 enormous galaxies that existed just 500 to 700 million years after the Big Bang. While astronomers anticipated the formation of star clusters shortly after the universe emerged from the Dark Ages, a period lasting roughly 400 million years when hydrogen clouds filled the cosmos, the sheer size and maturity of these galaxies have been shocking. One of the galaxies may have a mass 100 billion times that of the Sun. By comparison, our own Milky Way, with its billions of stars, has had 13 billion years to reach its current size. "It's mind-boggling," said Erica Nelson, an astrophysicist and assistant professor at CU Boulder. In a press release, she commented, "You just don't expect the early universe to organize itself this quickly. These galaxies shouldn't have had time to form." Nelson added that her team has been informally calling these objects universe breakers due to their staggering implications, and so far, they've lived up to the name. For a brief moment, this new evidence seemed to threaten astronomers' foundational understanding of the cosmos. Could the standard model of cosmology, our most established theory about the universe's origins and makeup, be incorrect if the starting point looked like this, especially since it didn't account for the findings of the Webb telescope? However, astronomers now believe that the theory can incorporate the surprises revealed by the new telescope. Recent computer simulations based on the standard model suggest that the universe might indeed have formed some of the galaxies discovered by Webb. Although the data may initially appear inconsistent with cosmological models, Ligia suggests that the real issue lies not with cosmology, but with our understanding of galaxy formation. There are many possible explanations for how astronomers might have misinterpreted the data. Perhaps early stars formed more efficiently than previously thought, driven by mechanisms not yet considered by scientists. Alison Kirkpatrick, an astronomer from the University of Kansas studying galaxy evolution, wonders if cosmic dust in these galaxies could be distorting Webb's observations, making stars appear older than they are. It's also possible that cosmic dust was different in the past. Ivo Labe, an astronomer at Swinburne University of Technology, believes that black holes could play a role. Black holes are some of the brightest objects in the universe when they consume cosmic matter, which glows as it is drawn in. When a large amount of gas falls into a black hole, it can become bright enough to outshine the entire galaxy, according to Labe. These black holes could cause early galaxies to appear brighter and more star-filled. But none of these explanations will change the fact that the first galaxies don't match our expectations. Even considering new, unexpected phenomena, everything is too large and appeared too soon, Labbe says. To investigate these questions, more Webb observations are needed, particularly those that provide detailed starlight measurements known as spectroscopy. Astronomers need further data to confirm whether the most unusual galaxies they've discovered are indeed as old and large as they appear. Understanding their composition will help astronomers learn about the conditions in which they formed. Researchers are currently analyzing data, with complete spectroscopic data expected by spring. This process is almost like a soul-searching journey. The demand for primordial starlight has never been greater, and astronomers and theorists, both those who observe and those who explain cosmic phenomena, aren't sure what they'll discover when their research is complete. It will likely take about 5 years to fully integrate the new understanding of the universe that we've gained from JWST, according to Ren Suss, an astronomer at UC Santa Cruz and Stanford. In one way, these discoveries have brought excitement and even anxiety to a field that had been relatively stable. As Nelson noted, it's astonishing how much stranger the universe is than we had imagined. Since it relates to the beginning of the universe, it's fascinating to think about these things. It's safe to say that the first year of observations from the James Webb Space Telescope Cycle 1 concluded spectacularly. Astronomers are astonished by what Webb has accomplished so far, but even more exciting results may emerge in its second year, Cycle 2. Just like Cycle 1, competition for Cycle 2 is fierce, and while there are plenty of winners and groundbreaking science to be done, many others missed out. Cycle 2 begins this month. Nancy Levinson, the interim director of the Space Telescope Science Institute in Maryland, which oversees the JWST, mentioned the remarkable response from the scientific community. In total, astronomers submitted approximately 1,600 proposals to STSCI for observing time on JWST, a NASA-led mission, but only 249 were selected. This results in an oversubscription rate of nearly 7-to-1, similar to the one experienced with the Hubble Space Telescope. To reduce potential bias, the selection process for JWST's programs is entirely anonymous, with hundreds of astronomers from various subfields contributing to the decision-making. That said, there were some clear winners and losers. For example, Nathan Adams from the University of Manchester in England submitted several proposals that were ultimately rejected. "We had 4 proposals and none of them got time," Adams said. "Obviously, we're a bit disappointed," he added. On the other hand, Marianne Leimbach from Texas A&M University had a much more successful outcome, with 3 of her proposals approved. "We're excited about the time we got," Leimbach said. Her proposals focus on white dwarfs, Earth-sized remnants left behind when stars like our Sun expand into red giants and shed their outer layers. It is believed that these stellar remnants might still host intact planets, providing an opportunity to study them and gain insights into Earth's future, when the Sun will enter its red giant phase in about 5 billion years. Leimbach plans to confirm 2 suspected white dwarf planets and search for up to 6 more in other parts of the sky. She explained that JWST could detect if any of these nearby white dwarfs appear brighter than expected, which could suggest the presence of a planet.